Something that was fully saturated would have just single bonds. Last term we talked about, what was it called? The
degree of unsaturation.
Yeah, degree of unsaturation, which basically told us how many pi bonds there were, or maybe also rings, but that was kind of a similar idea. The unsaturation is where you have these pi bonds from a double bond. So this is called alpha beta unsaturated because there's the double bond between the alpha and the beta carbon. Notice that the beta carbon is the former carbonyl carbon as well. Of course, we could have done this with a ketone, and then we would end up with an alpha beta unsaturated ketone. All right, so that's this product over here. This is still called an Aldol reaction, even though we don't end up with an alcohol anymore. Even though we don't end up with an alcohol in this product, it's still called an Aldol reaction. Also, it's called the Aldol condensation. Aldol condensation, condensations are where two molecules are coming together by losing a small molecule. Well, here we're coming together by losing the hydroxide. So, okay, so there's a bunch of different names for this. Now, this is, again, something we have to recognize as a hidden carbonyl. We have to recognize that if we see an alpha beta unsaturated aldehyde or ketone, that could have been produced by a forward aldol condensation, so we can also get that to be a reverse aldol condensation. Retroaldol. So we just need to train ourselves to watch out for these two patterns. Beta hydroxy aldehydes and ketones, or alpha beta unsaturated aldehydes and ketones, and we need to recognize that those would be good starting materials for retroaldols. What would we have to add to make this do the retroaldol? Similar to what we did for the previous retroaldol that I mentioned.
Heat, you had said.
Yeah, heat and hydroxide. We'd have to add heat and the base catalyst, although I don't know if people always mention that. We need the hydroxide to put the carbonyl oxygen back on. And then that would just zip us back to the two separate aldehydes again.
Even the, so that's why it's in equilibrium, because in heat, like you can go back and forward.
Yeah. All right, let me just mention one more time that I think it really helps people to avoid mistakes to keep labeling the alpha carbon, that's the nucleophile, and keep labeling the former carbonyl carbon and former carbonyl oxygen that was acting like the electrophile in all your pictures. That helps to avoid many common mistakes. Any questions? All right, so we should do some more practice with this. First of all, let's take a look at the handouts. Okay, so the Aldol condensation is on page 4. Yeah. So we show on page 4 of the aldehydes and ketones handout how you can either have a category 1 or a category 3, depending on whether you have cold conditions or hot conditions. But in both cases, it's base catalyzed, and in both cases, the nucleophile is the alpha carbon from an enolate, here on page 4. And in the left-hand columns, we have the mechanisms. We just went through the mechanisms, and they show that the products are either the beta hydroxy aldehyde or ketone, or the alpha beta unsaturated aldehyde or ketone. And then in the right-hand column, they have the mechanisms for the reverse reaction, which maybe we won't have time to go through today, but you would be expected to know that as well. Remember that in the right-hand column, you should read the mechanism from the bottom up. That way you can see how it's really just reversing each of the steps on the left-hand side. If you compare the right-hand column and the left-hand column, you can see each step on the right-hand column is just the reverse of the step that's in the left-hand column, so that should help to make it a little bit easier. And again, I think it's important to keep labeling with the asterisk and the alpha carbons, so I mentioned that there. Oops. So let's draw the mechanism for this reaction. Don't forget that this has a negative charge.
I'm doing that.
The hydroxide has a negative charge. Now, in this last step, you showed the enolate forming simultaneously with the leaving group leaving. Again, like we said in the textbook, they actually show those as two separate steps. So on the test, that might be a safer way to draw it. In the textbook, they show first the enolate forming, then the leaving group leaving. That would be more consistent with our first step, where first we form the nucleophile, and then the leaving group leaves, even though I've seen it drawn the way that you had it as well. I think this is maybe a little safer. All right, well, that's good progress. And again, I think it's really helpful to keep putting in these asterisks and this alpha symbol over here to show who was the electrophile and who was the nucleophile. I guess these are really all reversible steps. If this had been under cold conditions, we would have stopped with this product. Under cold conditions, we would stop with this product. What would be a good name for this product over here? The general type of functional group?
Alpha beta unsaturated ketone.
Yeah, this is our alpha beta unsaturated ketone. And what's this?
Beta hydroxy ketone.
Yeah, this is a beta hydroxy ketone. Good. And again, both of these could do retroaldols. Suppose these are both hidden carbonyls. Suppose I wanted to turn this back into ketones, what reaction conditions would I use?
Base catalyst, which we have, and heat.
Yeah, you'd have to add the base catalyst and the heat, and then brings it back to here. Notice that in this case, I just drew the one aldehyde, but we have to know that there's still billions of these, so you can have one aldehyde attacking another one, or actually I drew one ketone. Something else we should have talked about before is, you guys mentioned that we have a weird leaving group here. It seems a little bit weird to have a hydroxide leaving group. Even though that can sometimes happen, there has to be a reason for that. For example, last term we had oxide leaving groups to relieve the ring strain in epoxides. So we need to have some reason for this hydroxide leaving group forming. And the basic motivation of this here, this is an important point. This is what we call a conjugated molecule.
Oh, yeah.
Have you guys heard that term? That's going to be another big theme in this course. Conjugated, one of the definitions of conjugated is alternating single and double bonds. One of the definitions of conjugated is alternating single and double bonds. Well, here we have these double bond, single bond, double bond. Double bond, single bond, double bond. That's an example of conjugation. There's actually a better definition of conjugation that we'll get to later in the course, but a good initial definition is alternating single and double bonds. The important thing is, does nature like conjugation?
No.
Yes, nature loves conjugation, and one simple reason for that is it gives you resonance forms. When we have, there's a bunch of different resonance forms we can draw here.
Just keep on moving.
That's right. So like benzene that has resonance forms, conjugation, alternating single and double bonds gives you resonance forms. Does nature like having resonance forms?
Yes.
Yes, because it allows it to delocalize the electrons. The more different places we can put the electrons, the happier nature is going to be. So resonance forms are good things. So conjugation is a good thing because it gives us resonance forms.